So, Chapter 2 quiz, half-life. Rylan, half-life is a tricky concept for two reasons. First of all, the mathematical concepts of it are tricky. But the second issue is the counting. There's something in computing that we talk about. It's called a fence post error. I'm going to pick on you. You ready? Rylan, my friend, if this is a fence, there's a picture of a fence. If this is 1 meter and this is 1 meter, how long is the fence grand total? Give me the obvious answer. A 2-meter fence, but how many poles does a 2-meter fence need? 3. The problem we have, Sage, is kids aren't sure whether I'm counting these or whether I'm counting the gaps. They aren't sure which one is which, and so I'm going to try and give you a method that makes that clear, but I got to pause because someone just came in late. Push between what we're counting. So here we go. The half-life of cobalt is 5.26 years. How many, come on, there we go. How many half-lives have passed in 10.52 years? Now, some people might say, oh, well, if one half-life is 5.26 and this is twice as big, the answer is 2. But I'll show you a less intuitive, more systematic way to get there. So what I do is this. I say, there's a loop, that's 1 half-life. That's 5.26 years. There's another loop. That's 2 half-lives. That's 10.52 years. So in my drawings here, Julie, each loop is a half-life. Not each of these. I'm not counting those. I'm counting each loop as a half-life. It's 2 half-lives. And I'm going to keep flogging that approach, Dylan, to see if I can use it to bail me out of the rest of these questions as well. Number 2. 12.5% of a radioactive sample are left. How many half-lives have passed? We're doing percentages, so my picture is going to look like this. Now, when I'm doing percentages, what percent do I always start with? So here's 1 half-life. What percent is left? 50. Here's another half-life. What percent is left? Here's another half-life. What percent is left? And I hope now by drawing a little picture you can see it's a little more obvious how many half-lives have passed. Altogether, 3, not 4, 3. 3. Okay. Number 3, after 3 half-lives, how much of a 400-gram sample of radioactive uranium remains? How many half-lives? So I'm already imagining 1 half-life, 2 half-life, 3 half-life. I either put the number of half-lives, or if they actually tell me how long a half-life is, I'll put the time up there. But that's where I label my half-lives. Now, for a percent, I said we start with 100. Here it's not a percent. They gave me grams. Joseph, how much should I start with?
400.
After 1 half-life, how much will be left?
200.
Then?
100.
Then?
50.
Final answer? 50 grams. Number 4 is number 3 done backwards. In number 3, I told you what we started with. How many half-lives? What did we end with? Here, in number 4, I'm telling you what we ended with. How many half-lives? And I'm asking what we started with. So I'm going to use a similar approach, but it's going to be backwards. Julia, instead of starting here and going this way, I'm going to say, they told me we finished with 10. There's 1 half-life. Going backwards, what must I have had beforehand? 20. 40? 80? You know what I had 4 half-lives ago? 160 grams. Now, when people handed in the homework from 7.2, when I glanced at that front page and I didn't see any of these loopy diagrams, I went, okay, I'm going to give you guys a quiz on all of it because it's pretty clear people copied stuff. This is going to be probably about 25% of your test, by the way, this quiz and similar questions. Number 5. How old is an artifact if 4 half-lives have occurred? And the half-life, should be half-life, typo, of carbon-14 is 5,070 years. 5,070? 5,730 years. Okay. How many half-lives? 1, 2, 3, 4. Now, I could label this, don't write this down, 1, 2, 3, 4. But in this case, they told me how long a half-life is. How long is each half-life? You know what? It's going to be 4 times 5,730. And this is why you need a calculator. Or you could go 5,730 plus itself 4 times, because that's the same as timesing by 4. That's how old this particular object would be. 4 half-lives. You get 22,920 years old. How much time has passed if carbon-14 has a half-life of 5,730 years and 2 half-lives have passed? $5,730, $5,730. You know what? It's going to be, can I do this in my head? 11,460? Is that right? Years. I guess I should put units there. Years. Okay. Now, if you had trouble with this quiz, please don't be copying this out. I'll put the answer key online. You can still try it yourself from memory in a day or two or on the weekend. Mark it yourself and email me the score, right? A rock, oh, okay. A rock that originally had a mass of 1 gram of uranium-238 now only has 0.125 grams. How old is the rock? We're starting with 1. After 1 half-life, how much is left? 0.5. I got to stop when I get to 0.125. So, I keep going, Julia. What's the next one going to be? I keep going. Ah! There it is. How many half-lives? Ty, can you see? 3? What's 1 half-life? 4.5 billion years. 4.5 billion years. 4.5 billion years. You know what? It's going to be 3 times 4.5 billion years. It's going to be 3 times 4.5, 13.5 billion years. Excuse me. Mercury 197, Hg 197, has a half-life of 3 days. Check. What percent would be left after 15 days? Sage, what word did I underline? Which means I always start with 100%. How many half-lives is that, Sage? 1. How many days is 1 half-life in this question? 3. Now it's 6 days, grand total. When am I going to stop? How many days do they want me to go for? 15. There you go. 9, 12, 15. I guess it's 5 half-lives is another way to think about it. So you ready? 100, 50, 25, 12.5, 6.25, 3.125, is that right? 3.125%. The rest of the mercury would have decayed into its daughter isotope. I don't know what mercury's daughter isotope is. Only 4 or 5 are the ones on your purple sheet. But so this, if you started off with 100% of mercury 197 after 15 days in that bottle, only 3.125% would be left of mercury. The rest would have transformed, would have decayed into something else. A rock sample starts with 120 grams of a radioactive isotope with a half-life of 25 years. I just made something up because I didn't want to use real-world examples. How many grams of the parent isotope are left after 3 half-lives? By the way, 3 half-lives, how many years in this question? $75, 1 half-life is 25 years, so 3 half-lives would be 75 years. I could have said, instead of 3 half-lives, I could have said after 75 years. Anyways, how many half-lives? 1, 2, 3. Starting with 120. 60. 30. Answer, 15 grams of the parent. By the way, how much would there be of the daughter? Whatever 120, well, 105 grams would be daughter isotope. Sorry for YouTube as I'm coughing. Is that okay, Ty? Yeah. Let's keep going. How many grams of the, still wants the parent, are left after 100 years? Now, some of you may say, hey, I know that's 100 years is how many half-lives? I think since 1 is 25, it's going to be 4 half-lives. But if you can't do that intuitively, Andrea, start going loopy. I don't mean draw loops. We're starting off with 120. There is 25 years, 1 half-life. 50 years. Oh, sorry, I can't do math, Mr. Dueck. That's terrible. 60. 30. 75 years. 15. 100 years. You know what? 7.5 grams of the parent are left. How much of the daughter is left? Well, we started off with 120 grams. We have 7.25 grams of the parent. The rest must have decayed into the daughter isotope. 112.5? Is that right? The half-life of nickel-28 is 6 days. What fraction of a sample of this isotope will remain after 36 days? By the way, how many half-lives are we talking about here if 1 half-life is 6 days and the total time is 36 days? 6. And again, if you can't see that, go loopy, metaphorically. So, what am I starting with? Did they tell me? Courtney, did they tell me how much we're starting with? Say no. No. Is this a percent question? Did they say, okay, if it was percent, I start with 100. If it's a fraction, I start with the decimal version of 100%. What's 100% as a decimal? Folks, Math 8. What's 100% as a decimal? Don't overcomplicate it, folks. 1. That's what I'm starting with. And now I'm going to go fractions. A half. I'm going to go fractions. A quarter. Divide by 2. I'm going to go fractions, not 1/6, 1/8. I'm going to go fractions. 1/16. 1/32, 1/32, 1/32. You know what? 1/64 will be remaining of nickel 28, and 63/64 will be the daughter. By the way, it's worth learning your powers of 2, right? 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024, 2048, 4096, 8192, 16,000. Oh, come on, Dueck. 16,300 and something. I'm on medication right now. I can't think as good as I normally do. Excuses. It looks like, 2 marks each. So I think what I was doing here was if you had the right answer, you got 2 out of 2. Otherwise, I would give you 1 mark for the picture and 1 mark for the answer. 1 mark for your work, 1 mark for your answer. And I did that on purpose because, again, it seemed many of you were just copying answers in the homework. So if you can give yourself a level, 2 marks each. Yeah, that works because then it's 18, 20, 22. Is that 24, 26? 16, 26, 24. Okay. Can you give yourself a lovely score, please, out of, count them, 24. So last day, we finished off looking at nuclear reactors. It was, and again, I keep picking on Julie because she was the one who brought it up in the very first lesson. Does it get tougher? You can see it's the same kind of equations, but I have to be able to interpret a little bit more. Okay? So the homework that I gave you was section 7.3 homework. There was some vocabulary stuff. But what you're really going to have is a bunch of these. And I may ask you to distinguish what's going on. Oh, neutron means that's a nuclear reactor. It's either fusion or fission. If you see a beta particle, that's beta decay. If you see an alpha particle, it's alpha decay. If you see the asterisk and the funky energy thing, that's gamma decay. So I would have no problem giving you a bunch of equations and saying, hey, which one of these is alpha decay? Which one of these is beta decay? Which one of these is gamma decay? Were there any questions from the homework here that you wanted me to go over? Now is your chance to ask. Yeah.
Back on those equations.
Yeah.
I noticed that some of them, on number 1 there.
Yeah.
The answer you put a 3 there beside the neutron on the end.
Yep.
And then a couple of examples it was a 4.
Yep.
How do you determine that number?
First of all, we're being intellectually honest in that when a chain reaction happens and an atom splits, when uranium splits, usually it gives off 3 neutrons, but not always. So we did a couple. So you ready? It all has to do with the mass. Ready? What's 1 plus 235? Okay, so the amount of mass that I have on the left is 236. How much mass do I have to have on the right? 236. I got 152 here, and this is 4 neutrons. So this is 152, this is worth 4. So what's left over for mass? 236 minus 152 minus 4. This has to have a mass of 80. So going to your question, for example, how do I figure out what number goes there? How much mass on the left? How much mass on the right? Has to add to 236. Right now I have 143 and 90. I got 233. Because each neutron is worth what? 1. So I'm saying you need 3 more of those, otherwise your mass doesn't balance. Does that make sense?
Yeah.
Okay. Looking at number 9, for example. By the way, most of the time you're going to start with 236 because we're splitting uranium and we're trying to be intellectually honest. That's the most common one. Add those 2 together. Whatever's left, that's how many neutrons that you're going to need. Is that okay?
Yeah.
So you can work on that. Any other questions from the homework? Yes.
When you're doing the fusion and fission equation,
Yep.
how do you know if it's hydrogen or if it's helium that has to be in the blank?
In the blank here?
Yeah, well, there, and then the other one is
Number 2?
hydrogen, like number 4.
Like number 4? Sure thing. Okay. The element, the symbol, the carbon, the nitrogen, that always comes from the bottom number because that's really telling you not just how much charge there was, it's saying really how many protons you got kicking around. So certainly for mass, I got 2 plus 2, 4. I got 3. It's got to be 1 for the mass. Starting out, I had how much charge? How many protons? 2. I got 2 there. You know what? Oh, what has a mass of 1 and a charge of 0? It's got to be a neutron. That's what, apparently, this particular reaction, its hydrogen is combining into helium, and it also spits out an extra neutron when that happens. Okay? Or, say this one here, 2 plus 3. Oh, you know what? This is good. I can tell you right now this is going to be a neutron again because I got 1 plus 1. I got 2 here. It's going to be a neutron. Let's see if I can find a more interesting one here. One at the very top? Number 2.
Yeah, that one.
Okay? So, on the right-hand side, I have 1 plus 1. I have a total of 2 protons kicking around. You know what? I only started with 1 proton. I must have had 1 extra proton. What is 1 proton? It's got to be hydrogen. It's the only element out there that has a charge of 1, that has 1 proton. What must its mass have been? Now, this is kind of a funky hydrogen because normally on the periodic table, what does hydrogen have as its mass? I got one in front of me. Has a mass of 1. This one has a mass of 2. And what we're saying is inside stars, in particular, in fusion reactions, the pressure is so intense, often hydrogen will pick up an extra neutron because there's just crazy stuff going on inside there. In fact, sometimes it even pick up 2 extra neutrons, which is how later on you could have a hydrogen with a mass of 3. It's got 1 proton, and you know what? In its nucleus, 2 neutrons have been stuck in there under the tremendous heat and tremendous pressure of the gravitational field of a star at the center of the gravitational field. Is that okay? I didn't hear a phone go off there, did I? You sure now? I thought I did. So what are we working on in class today? I'm pressing pause. What I have for you, though, is 2 quizzes, and one I have here. It's going to be a bunch of the, first I'll identify whether it's fusion or fission. Key idea, fusion, 2 small atoms, usually hydrogen or helium, combining into a bigger atom. Fission, 1 big atom splitting up into smaller atoms. And then balance the equations. I'm going to give you that quiz. I put some more half-life stuff. These half-life, number 2, I lifted right from the test and just changed the numbers. That's a hint. Oh, I have an element called ribalcium. We all know you're radioactive. Yeah. And then I also have a review quiz on everything, and I think I left it upstairs when I photocopied it, so I'm going to go get it in a second. Otherwise, I'm going to have to make new copies. Let me hand out this first one.